So Hess's law is a little confusing at first, but it's fun. So basically it's like if I give you multiple reactions, like A goes to B, and I told you delta H for this, delta H1 was 10 kilojoules per mole reaction. And then I gave you, B goes to C. And when that happens, delta H is 20 kilojoules. Well, that's fine. Kilojoules per mole reaction. Then you would say, okay, well, if I add these together and I get A going to C, then it makes sense that the overall change in enthalpy will be a combination of those, and that is correct. Okay, so you're basically adding equations together to get like a target equation. And you would be adding together equations whose delta H's you know to determine the delta H for an equation that you don't know. This can be a little trickier sometimes if you have something like this. You might have like C goes to B, and then these equations don't add the way that you want them to. So in order to get them to work the way you want them to, sometimes you have to flip them and do the opposite reaction, like reverse it. And when you do that, you have to modify the value of its H. Okay, you have to multiply it by -1. That should be times -1. Okay, the other rule that we're going to have to bear in mind is that sometimes in order to get things to add up right, you have to multiply an equation by some other number, like to get things to cancel the way they need to. And if you do that, you need to also multiply the delta H by the same number. So let's do an example that might help. This is our target equation, okay? What is delta H for this equation, okay? We know delta H for these two other equations, okay? And you can see that they have some of the same stuff. We're gonna try this again. They have some of the same stuff in them, like diamond, carbon as a diamond, and carbon as graphite in it, but there's all this other stuff also. So we need to find a way to add these together so that everything cancels except for diamond and graphite. And we want diamond to be a reactant, and we want graphite to be a product in our final overall reaction. So if you look for a distinctive thing in your target reaction and look for it in one of the given reactions. Diamond as a reactant is what we want. So this, and we want 1 mole of it, right? Because there's 1 mole here. So we're actually probably going to leave this equation the way it is because diamond is a reactant and there's 1 mole of it and it kind of looks the way we need it to. But how do we get rid of all this other stuff? So look at another distinctive thing in the target reaction. Graphite as a product. Okay, graphite is here, except it's a reactant, and up here it's a product. So we're gonna have to flip this whole equation around. Maybe I'll have to write this in a different color so it's more clear. We're gonna flip this whole equation around, okay? I'm gonna do times -1. I'm also gonna do its delta H value times -1. I'm gonna rewrite it this time. I won't always do that, but just to try to make it more clear how everything cancels. Okay, so we have CO2 now is going to be the reactant instead of the product, and carbon as graphite is going to be a product instead of a reactant, which will help us get closer to this target reaction. Okay, and then delta H is going to have a positive sign because we flipped the reaction around. We changed the sign of delta H. Let's see how we're doing on this. Oh my gosh, is it still going? Okay, let's just change this to white because it looks sort of gruesome. Okay, when we do this, we're going to cross off this top one because we don't need it anymore. When we do this, we'll see that graphite is a product now, like we want it to be. Okay, I don't know why the highlighter is so finicky. Why doesn't it draw over that? Oh, that's weird. You guys probably understand it and I don't. Okay. Lucas, can you explain it to me? No, I couldn't hear his explanation. Oh well. Okay, so you guys notice that O2 is a reactant here and it's a product here. So we're going to cross it off because it's like if you have X on both sides of a mathematical equation, they cancel. Okay. We also see that CO2 is a product here and CO2 is a reactant here, so they cancel. So what you're left with, if you try to add these two reactions together, if the CO2 and the O2 both cancel, you're left with diamond goes to graphite, which is the exact same as the target equation that we were given. So now that we've done that, Alex, what do we do with the delta H's? Good, we add together the modified delta H values. That's right. So we get 1.9 kilojoules will be the delta H for this new reaction. So this was a way of finding delta H for a reaction, is by, honey, buddy, I can't talk right now, okay? I'm making a video. No, love you, bye. Okay, oh, they're crying. Okay, so hard to focus. Okay, so if you're trying to find delta H for a target reaction, you have to make sure that the reactions you were given can add together in a way that all the excess stuff cancels out and you're left with just the same reactants and products that you have in your target. Whatever modifications you had to make to the reactions, you make those modifications to their delta H's and then you add them together. So this is why this makes sense conceptually, is that the change in enthalpy associated with carbon and graphite combining to, graphite and oxygen combining to form CO2 is here. That was this reaction number 1, right? And then, this is the, once the first reaction gets flipped around, those are the products, right? And then this is reaction number 2, the way that it's written, where diamond becomes CO2. So basically, if you have diamond and O2 becoming CO2, and then going back to graphite, the shortened version of that is this. Okay, another practice problem. More graphite and O2 and CO2, but sort of a different setup, okay? If you want to pause these and try them on your own, I really highly recommend that. Otherwise, I'll just kind of keep going. So, Maggie, do you see any reactant or product in our target reaction that only shows up one time in the given reactions? Maggie says graphite, and Maggie is correct. Okay, so graphite, graphite is a good thing to start with, okay? It would be really confusing to start with O2 because O2 shows up in multiple places in the given reaction, so you wouldn't know which of those you had to modify to get, like we want to have 1 mole of O2 in the reactants, but how would we do that given O2 in both of these other reactions? So we're not going to look at that. We want to look at things that are distinctive and that only show up one time. Arena, can you see one other thing that's distinctive and only shows up one time in the given reactions? Yeah, good. The CO2 only shows up one time. So if we kind of get both of those to do what we want them to do, to be where they need to be, then hopefully everything else will fall into place, and it always does. It always works out. Okay, so let's look at graphite first. We need to have 1 mole of graphite in the reactants. Oh, that's nice. We have 1 mole of graphite in the reactants. Isn't it nice when they start easy? Okay, so perfect. This reaction is going to stay the way it is. We're not going to reverse it. We're not going to multiply by anything, and this delta H will also stay the way that it is. Okay, our other thing of... Our other species that we're focused on is gaseous CO2, not CO, right? Just CO2. Here, CO2 is a reactant, and up here we need it to be a product. So we're going to try flipping this guy around, and I'll just show the whole thing. Times -1, if it helps you, and eventually you'll stop doing this, but you can do it at first, is you can, I'm not going to write this, so it doesn't matter, rewrite the equations. And sometimes it helps to even align the arrows so that it's really clear what's a reactant, what's a product, okay? Our delta H, when we flip the reaction, we need to change the sign, okay? And when we do that, what do we get in our reactants? He says you have graphite, that's correct. And what else, Will? 1 whole mole of O2, because 1/2 is 1 whole. And also you will notice, thank you, Will, that our CO cancels here and here, so that's not in it anymore. Okay, and then what do our products end up being? Lizzie, just little CO2 by itself. And Lizzie, how do we find delta H then for this target reaction? Yeah, good. We add up these two modified. Well, one of them wasn't modified. One of them was. We add up these two modified reactions. Okay. 283.0. Okay, 393.5. Okay. Go ahead and try this one on your own and then come back. We're just going to go ahead and start. Okay, Maya, go ahead and find a particular species up here that does not show up multiple times in our given reactions. Okay, Maya says CuO. Well, never mind, Maya didn't say that because that's wrong. Maya says Cu, and she is totally right. Okay, CuO actually shows up here and here, so wouldn't that be confusing because you wouldn't know which one to modify? Okay, CuO is going to fall into place if the Cu and the O2 are in the right places. Okay, so Maya says also O2. She's totally right. Okay, so we're going to try to get Cu and O2 into the right places with the right coefficients and then hope everything else works out, and it always does. Okay, so our first thing we're going to look at is Cu, which here there's two of them and it's a reactant, whereas down here there's one of them and it's a product. Okay, so we need to take this equation, we need to flip it and multiply it by 2. So I'm going to write times -2, and we're going to do the same thing for its H value. Okay, I'll write it out just because we're still learning. 2Cu plus 2CuO, everything gets doubled, goes to 2Cu2O. Okay, and our delta H for that will be -22 kilojoules. Okay. Maritza, what's our next step? Maritza says you should try to make sure that O2 is in the right place. Good idea. Okay, right now O2 is a reactant and there's one of them. Here, O2 is a product, but there is one of them. So we don't need to multiply this by anything, but we do need to flip it around. We're going to do the same thing for its delta H. Okay, again, we can rewrite it to make sure that we're understanding how this works. It's easier to cancel stuff. So we're going to write our products as reactants. We're going to keep our arrows aligned. We're going to write 4CuO, and we're going to write that delta H is now -288 kilojoules. Okay? Peyton, what's our next step? Okay, add and cancel out. Good. So when we do that, we see that okay, Cu2O cancels out, which is good because we don't want that in the overall equation, right? And then we see one other tricky thing, which is that CuO doesn't cancel, but it is on both sides. So we actually cancel some of them. Like if you had X on one side and 2X on the other side, you'd subtract X, and you end up with just X on the right, okay? So we're going to cancel out this and turn this one into 2 because you subtracted 2 CuO from both sides. Okay, when we do that, we will get 2Cu plus O2 goes to 2CuO, and shockingly, it works out just like it always does. Okay? I did that in my head. Might be wrong. Okay. So that's Hess's law. Okay, there's a whole Hess's law worksheet. They're actually fun. They're like little riddles. I think they're fun. I think some of you probably think they're fun too. It's okay to admit that. Okay.